All right, I want to take a look at the functions that we have dealt with over the last 2 units, radical functions and exponential and logarithmic functions. So first off, let's take a look at a square root function. Now the square root function, unlike polynomials and quadratics and absolute values that we had dealt with in the past, this is the first function where the domain and range are naturally restricted or limited. Now you hopefully recall that a square root function, a square root graph, looks something like this. It's sort of a sideways half a parabola. Actually, that's exactly what it is. And so what happens is the y's are limited, the x's are limited. How come? Well, remember we talked about this. If you're taking the square root of something, I have to take square roots of numbers that are 0 or positive, because if I try and square root a negative number, then I get imaginaries, and I can't map to the imaginaries with a function, not if I'm staying in the real plane. Also, when I take a square root, if I just focus right there on the square root of x minus h, well, as we talked about, when you take a square root, it's only talking about the principal square root. So for instance, the square root of 9 is just 3. I would never get negative 3 out of that, which is why I have naturally limited y values. So if I am asked about the domain, range, or for that matter, end behavior about a function, having a general sense of what the function looks like is honestly enough. Okay, so I'm going to make a little sketch of what this should look like. I can see right there my transformations. This is a square root function that has been vertically stretched by a factor of 2. It has been shifted left 3 units and down 5 units. So if I go left 3 and down 5 units, I will have this little terminal point right about here, and it's stretched by 2, but that's not going to do necessarily a whole lot. I get something like that, and I'll label this point negative 3, negative 5. So for increasing, decreasing, as well as domain, range, and end behavior, this sketch is enough. And again, I could use a calculator to confirm that this is what it looks like, but this sketch is really all I need to know, because the domain, I'll label, is, well, the smallest that x can get is negative 3. So I go from negative 3 to infinity. This is in interval notation. I can write bracket negative 3 to infinity. As an inequality, I could also say x is greater than or equal to negative 3. We need to understand both of those. For the range, how small do the y's get? Well, the smallest that the y's get is negative 5. And then I go up to infinity. All right. Let's take a look at another example. H of x down here. Well, perhaps the biggest difference you should notice right here is that this has been reflected. The transformations to this square root function are a reflection in the x-axis and a vertical shift 2 units up. So I will have a function that looks something like this. It's just a rough sketch. This is 0, 2. So when I'm figuring out domain, range, end behavior, again, all that stuff I can figure out just from this little sketch. If I wanted a y-intercept or stuff like that, frequently I would have to do a little bit of work. This is an exception because 0, 2 is the y-intercept. My domain, x is greater than or equal to 0, so bracket 0 to infinity. My range, well, the smallest y values are very small, negative infinity. The largest they get, however, is 2. So pay attention to that. When we write domain and range, remember it's always smallest value to largest value. So negative infinity to 2, or negative infinity is less than y is less than or equal to 2, or simply y is less than or equal to 2. What about a cube root? Cube root we haven't talked about recently. A cube root, less interesting graph, because its domain and range are not restricted. I can cube root negative numbers, and what's more, if I do cube root a negative number, I get a negative number, which means my domain and range are not restricted. They are both all real numbers, or if I'm in interval notation, I would say negative infinity to infinity. So if I wanted to know what's happening with these, I'm going to make sketches of these. I'm not going to write the domain and range, because everything that we do with these in this class, we can expect the domain and ranges to be the same. So here I go 2 to the right and down 3. 1, 2, 1, 2, 3. That's right there. And again, we're not really worrying about the points that are on these because we're not going that in depth. We're just saying, what does it generally look like and what can I glean from that? So it has this inflection point at 2, -3, and I could tell, for example, that it is increasing over its domain, and I can see its end behavior. This end approaches positive infinity, this end will go down towards negative infinity, and it might not be as flat as I have made it look like. That's just the fault of my sketch. And let's go ahead and take a look at the next example right here. Well, here again, I look at the transformations. 1, 2, 3, 4, 5. X plus 5 means I go 5 units to the left. I have not moved up or down, so I will go through like this. And then what I want to do, well, there's a nice big stretch on this thing. So I should see something maybe that looks like this. How important is the accuracy of that sketch? It's really not for anything I'm doing. I can see where that inflection point is. I can see that this is generally decreasing, but that's all I need to know. All right, so those are radical functions, and we see where the square root function, again, is naturally restricted. Let's move on. Let's take a look. Let's review exponentials and logarithms. So you have to think about it with this. You have to think about the way we initially introduced this. And the idea was, if I had something like, I'm just going to scribble a little note right here. If I said y equals 2 to the x, well, as I take larger powers of 2, 2 squared is 4, 2 cubed is 8, 2 to the 10th is 1024, I could keep going. I keep getting larger and larger numbers. So as x approaches infinity, 2 to the x will also approach infinity. On the other hand, as I take smaller and smaller numbers, 2 to the negative first is the reciprocal 1/2, 2 to the negative second is the reciprocal squared, 1/4, 2 to the negative third is 1/8, and I keep going like that. 2 to the negative fifth would be 1/32. 2 to the negative 10th would be 1/1024. And what's going to happen, you might recall, is as I take these smaller and smaller powers of 2, I keep getting smaller and smaller results without ever reaching 0. So this is greater than 0 for all values of x. Apologize for the shorthand. So we need to keep that in mind. So what does this give us? What does this tell us about an exponential? Well, since it's greater than or equal to 0, that means the y's are bounded. I have a horizontal asymptote, meaning my range is restricted. For a logarithm is the inverse. So a horizontal asymptote, as x and y get switched, will become a vertical asymptote, which means that the domain is restricted. Now I'm going to go ahead and fill these out in terms of how you find them. So the asymptote for an exponential is determined by the vertical shift. So what I can say is y equals, the vertical shift is k. And again, the idea is whatever this is, as x moves either towards positive or negative infinity, depending on the base, this will approach 0. So 0 plus k will get closer and closer to y equals k. For the logarithm, the idea is the inside has to be greater than 0, just like this had to be greater than 0. Here the output has to be greater than 0. Here the inside of the logarithm has to be greater than 0. If that has to be greater than 0, well, when the inside equals 0, that's a problem. So my asymptote is x equals h. That is my asymptote for any logarithm. If you know nothing about exponentials and logarithms, you should know, if you know nothing else. If you know nothing, then you know nothing. But if you know nothing else, then you should know how to find the asymptotes of these things. All right, so let's think about these things. G of x equals 3 times 1/5 to the x minus 2 plus 1. Again, I'm going to make a rough sketch of what this looks like. Draw some axes. I can see that the asymptote right there, I can see that 1 staring me in the face. So the asymptote is y equals 1. Here I can see that I have 3 times 1/5 to the x minus 2. My base is 1/5. My base is less than 1, which means that I have an exponential decay. So as time goes by, this graph, as x approaches infinity, the graph will approach its asymptote. So I'm going to make a rough sketch again, which is going to look something like this. Getting really close to that asymptote. We know it doesn't touch it regardless of how close we draw it or how close it looks on the calculator or anything else a calculator might tell me. So it's a graph that looks like this. And again, I can determine end behavior, domain, range, all that stuff just based on this sketch. What is the domain? The domain of every single exponential function is negative infinity to infinity. The range, well, the smallest that the y's get is 1, or technically a little bit larger than 1 because it never reaches that asymptote. How large do they get? Really large. This is going to shoot up to infinity. It's exponential. This is exponential decay. Here we'd be seeing something more like growth if we look in the opposite direction. Don't let that confuse you. This is going to go up to infinity. This is an exponential decay. Recall, exponential decay means the base is less than 1, or strictly between 0 and 1, but it's never 0 or negative or 1 for that matter. And exponential growth would be something like this. The base is greater than 1. So for example, if I had y equals just something real simple, 2 to the x plus 5 or something like that, well, then what I would have, and we'll say minus 3. Draw some axes, negative 3. 2 to the x plus 5 is going to be shifted very far to the left, so I will see something that looks like this. And over here it'll get closer and closer to the asymptote. And that is exponential growth. Now mind you, exponentials can look like this, they can look like this. If I incorporate a negative, I stop talking about decay and growth, but I can still talk about domain, range, and end behavior with those things. Here I can see my domain is again negative infinity to infinity. My range is from negative 3 and up. So parenthesis negative 3 to positive infinity. What about a logarithm? Well, for a logarithm, just remember how these work. Make a sketch. Oh, that's not going to be a good sketch. It's the bad thing about doing these in one take. You make mistakes. All right, x plus 3. X plus 3 means that negative 3, x equals negative 3. Negative 3 is a 0 to the inside. X equals negative 3 is my asymptote. All right. The plus 2 will shift this up by 2. The log base 5 just basically influences how sharply this curves. And I'll see something that looks like this. Maybe not that sharp. But again, the rough sketch is really all I need to answer questions like domain and range. Well, again, we want to understand how this works. For a logarithm, the domain is restricted. The range is not. I can see the y's are going to get really small, and logarithmic growth is slow, but it does go towards infinity. So I'm going to go ahead and fill in the range is negative infinity to infinity. The domain, the smallest that x gets, is negative 3. The largest it gets is large, because it's going to go over to the other side. Mind you, of course, I didn't discuss it up above, but I could reflect this onto the other side of the asymptote. There is a way to do that, but it's not something we've really done in this class, so it's not something you really need to concern yourself with. For a logarithm, you can expect that the examples you're going to see will be like this. They will be to the right of the asymptote. All right, so if I have that idea, if I can make those sketches, then I can make this work. Now, mind you, again, in terms of this logarithm, I could make a graph that looks like this if I wanted to. If I can get my pen to work as well, that would also be helpful. So here's an asymptote. How would I get a graph that looks like this is the question. Well, clearly, my asymptote is something like x equals 2 or 3 or 4, something positive. So I'd have that. But the question is, how do I get this to go down like this? And there are two possible answers. And again, you can confirm all this with a calculator. So let's say, for argument's sake, this is x equals 2. I know inside I'd have to have x minus 2. All right. Well, how do I get it to go down like that? I have two possibilities. One is, of course, a reflection. So I try and insert that negative in front. So this might be, and that's a fairly slow curve, so this might be a base of 3 or something like that. But the other thing is, I could do the same thing, and you can test this with a calculator. If I used a base that is less than 1, again, I would see this kind of decreasing behavior. I would see a function that is decreasing. I'm not asking you to necessarily remember this, but it is good to think about the fact that the logarithm does not necessarily always need to go up like this. I could reflect it. I can get it to go down like this. And I'll show you that I can do this with a calculator as well. Turn this off. Okay. So if I have the log base available, I will show you math log base. And let's say right there I said 1/3. And then I had x minus 2. Now remember, when we graph this, the calculator is not particularly great at graphing logarithms. And my window is messed up because I was looking elsewhere. Pause for 1 second, zoom 6, there's my standard window. Okay, so I see something like this, and this makes it look a little bit sharper than that is. That's not a big deal. But remember, you can use the graphing calculator for this, but what you have to know is where that asymptote is, and even though the calculator stops right here, you need to understand it does continue. Since it gets nearly vertical, the calculator is not good at graphing it. But just like over here, it's getting really close to the asymptote, here it'd be getting really close to the asymptote without ever quite touching it. Okay. So once we have those ideas, let's talk about, if I give you a question like this, and so I said find the domain and range of each function, and I said make a sketch. Well, let's take a look at some examples. The first one, 1/4 3 to the x plus 2 minus 5. Let's make a sketch of what this should look like. So there's some axes. I can see the horizontal asymptote because this is an exponential. X is in the exponent. The horizontal asymptote is y equals -5. Since the base is 3, I would see exponential growth. And I happen to have done this problem already, so I know that the y-intercept is a negative number. But in terms of figuring out domain and range, it really doesn't matter where you put this. Because if I shifted it further to the left or to the right, the domain is still -infinity to infinity. And the range is still all the numbers, all the y values that are greater than -5. So -5 to infinity. Okay. I discussed this in class, but in class I only did examples that were not reflected, so I want to throw one of those in. I'm going to not do B right now, I'm going to do D. So here, -1.5 times the square root of x minus 4 plus 3. Minus 4 plus 3 means I need to go 4 units to the right and 3 units up. The -1.5 will be a reflection, and 1.5 is a small stretch, but I need to reflect it downwards, so I get something that looks like this. Probably not that much, but again, it looks something like that, and this point is 4, 3. From that, I can figure out my domain and my range. My domain is bracket 4 to infinity. My range, the smallest y value, is -infinity up to and including 3. So 3 with a bracket. Y's that are less than or equal to 3. How about a logarithm? Let's go ahead and take a look at C. 2 times the common log of x minus 3. Common log, that's base 10. So what am I going to get? Something like this. X minus 3 means 1, 2, 3. X equals 3 is my asymptote. Make sure you make a note of that. If you're ever graphing these, you know you need to graph the asymptote. If you want to analyze them at all, you have to know the asymptote. 2 is a vertical stretch. Common log, that's a log of base 10, so we would see a very sharp turn with this. But the 2 will make it look a little less sharp. It looks something like that. So what is my domain? Again, the inside has to be greater than 0, so x has to be greater than 3, so I say 3 to infinity. My range, well, the range goes from -infinity up, -infinity up slowly towards infinity. You got that slow logarithmic growth. So it'll look something like that. The rest of the examples are all doable in a similar fashion. Make sure to check the key. Referring back to these exponential functions, remember, this is enough. I've said it multiple times that you can figure out domain and range but also I've mentioned that you can do things like end behavior and increasing and decreasing just based solely on this without making a super accurate graph. I could figure out the end behavior of this. Here I can see that the end behavior as x approaches negative infinity, y approaches negative 5. As x approaches positive infinity, y, or f of x, approaches positive infinity. Think about stuff like that. Math is about understanding this stuff. All right, do a couple more examples right here, and then I'm going to call it a day. I want to identify each function as exponential growth or decay, determine its y-intercept and asymptote. Well, that's pretty easy to do. At least two of those things are. Is this growth or decay? Well, I look right here at the base, the thing that is being exponentiated, and 1/5 is less than 1, which makes this exponential decay. The asymptote is a horizontal asymptote. I'm going to label my work asymptote and give its equation, of course, is y equals, where do I look? Right there at that vertical translation. Y equals -3. The y-intercept, that takes a little bit more work. But remember, y-intercept, when you hear y-intercept, you got to think x equals 0. So to find the y-intercept, I got to see if I can cram my work in here because I have not given myself enough space. And that's my fault. 10 1/5 to the 0 plus 2 minus 3. Well, that's 1/5 squared. 1/5 squared, you square a fraction, you square the numerator, you square the denominator, which would give you 1/25. So this is 10/25 minus 3. 10/25 is 2/5. To convert 3 to fifths, I multiply by 5 over 5. Multiply by 1, that keeps it equivalent. That gives me 15/5. 2/5 minus 15/5, I wrote thirds. 2/5 minus 15/5 is -13/5. So my y-intercept is the ordered pair, -0, -13/5. And you do all the others in a similar fashion. And of course, mind you, if you need this fraction, your calculator can do that. You can just come right over here and say, well, you quit out of that first off, but you say 10, and in parentheses you say 1/5, and then you close those parentheses, and you raise it to the second, and then you say -3, and your calculator tells you -2.6. But if you need a fraction, you go to math and you change it to a fraction, and you get -13/5. All right, the other two are similar. I'll show you one of these. 25 to the 2x minus 5 equals 125 to the 3x plus 2. These are both powers of 5. 5 squared and 5 cubed. That's what gives me 25 and 125. What do I do with those? Well, these are being raised to the 2x minus 5 and the 3x plus 2, which means those exponents need to get multiplied. Now, since every power of 5 is unique, the only way this can be true is if these exponents are the same number. So 2 times 2x minus 5 is equal to 3 times 3x plus 2. Be careful when you solve this. Make your Algebra 1 teacher proud. 9x plus 6. So that means -10 is equal to 5x plus 6, -16 is equal to 5x, and x is equal to -16/5. And that'll do. All right, one last thing. Make sure to check your answer key, which will have the complete solutions. The value of a car depreciates. The demand for a new cell phone increases. These are both models of exponential growth and decay. If you are given a table of values, you use a regression. If you are given a word problem such as this, you start from the model a of t is equal to little a times 1 plus r to the t. Little a is your initial amount. R is the rate of growth or decay. Pay attention, because if it is decay, then r needs to be negative. And t is it's an x essentially in this function. This is a function of t. So the value of a car depreciates. Hopefully you understand that means that it is decreasing over time. If you buy a car for $9,500, it tells you that it is depreciating every year by about 14.5%. 14.5% is 0.145. Now you are asked for two things here. You are asked to write a model showing the value of the car after t years, and then you are asked to use this model to approximate the car's value after 5 years. So your model, which you should simplify this, is 9,500 times 0.855 to the t. That is your model. If I want to figure out the value of the car after 5 years, that means I'm going to substitute 5 for t. So I go to my calculator and I say 9,500 times 0.855 to the fifth, because it's 5 years. And that gives me this number. All right, so A of 5 is approximately, no rounding instructions here, so generally you would go to the nearest cent, although be prepared, because if this is a multiple choice test, you may well have an answer choice that is to the nearest dollar. To the nearest cent, I have 4,340.64. So in 5 years, you lose nearly half your investment. Yeah, that's about right. All right. Next one is similar. The demand for a new cell phone increases by 8% every month for the first year after its release. I'm just going to do this silently. That's it. 450 phones upon release. After 8 months, with that 8% growth, we can expect that in the 8th month they will be selling 833 phones. Don't tell me this problem is not realistic. I already know that. Hopefully this has helped.